Welcome to Lecture 3 of the course Wireless Communication at Chalmers University of Technology. My name is Henk Wijnmeers. In this lecture we will talk about narrowband time-varying channels. We will first discuss Doppler shifts and then time-varying channel impulse responses. We then look at time-varying narrowband fading models, the Rayleigh and the Rice model, as well as the Jakes model. Finally, we talk about level crossing rate and average fade duration. This lecture relates to Chapter 3 of the book Wireless Communication by Andrea Goldschmidt. Learning outcomes of today, you should be able to distinguish between wideband and narrowband communication, derive Doppler shifts, define resolvable paths, express the general formula for time-varying channel, explain the difference between Rayleigh and Rician fading, and define autocorrelation and power spectral density of wide-stand stationary fading processes. Last time we talked about the models for path loss and shadowing. So please recall that path loss is the decay of power with distance. It is a deterministic effect, and the most simple model is the one written here, where the received power is the transmitted power multiplied by constants divided by the distance raised to the power gamma, where gamma is the path loss exponent. In addition, we have shadowing due to large obstacles. So these are the large-scale variations of the power, which we model as a random variable in the dB domain with zero mean and a variance sigma squared. The total received power is then the transmitted power plus path loss plus shadowing. In addition, we have the small-scale variations of the power, which is called multipath fading, and this is due to mobility and the impact of the environment and small objects. We've seen last time that when a signal is sent from a transmitter to a receiver, depending on whether the receiver is wideband or narrowband, we will see many paths or a single path. We also mentioned that when the receiver, transmitter, or the environment moves, then the signal varies over time. This is the received power as a function of time. And the rate of this variation depends on the relative velocity of this transmitter with respect to the receiver. So in this case, the channel is varying slowly, so this corresponds to slow velocity. In this case, the channel is very more fast, so things are moving more fast. When everything is static, the channel would be some fixed number, would be flat in the time domain. In order to understand time-varying channel, it is important that we look at the Doppler shift. So we consider a transmitter far away, so that we're in the far-field regime, so we have planar waves, and we have a receiver which is moving in a certain direction. The transmitter is sending a signal with a certain carrier frequency Fc. Depending on the speed and the relative direction of transmitter and receiver, the received frequency will be the carrier frequency plus a Doppler shift. This is a well-known effect, for instance, that you get when an ambulance approaches you or drives away from you. This Doppler shift depends on the speed of the receiver multiplied by the cosine of the angle of transmitter with respect to receiver. This is because when the receiver is moving perpendicular to the line, so if the receiver moves in this direction, there is no Doppler shift. This cosine can be positive or negative depending on whether the receiver is moving away or towards the transmitter. The carrier frequency divided by the speed of light is the wavelength. So overall, the Doppler shift is the velocity of the receiver times the cosine of the angle between transmitter and receiver divided by the wavelength. We see that the Doppler shift becomes increasingly important for very small wavelengths or very high carrier frequencies. The Doppler shift creates effects that the channel will change over time. In the bottom, we consider a scenario with a transmitter and a receiver and different objects in the environment. On the figure on the left, at a certain time t1, we will see three paths. Each path has an amplitude, a phase, and a delay. Of course, paths further away will probably have less amplitude, but definitely a larger delay. At time t2, the receiver has moved away, and maybe one of the objects is no longer visible or has been removed, and we only have two paths with different amplitudes, different phases, and different delays. So due to this, the channel changes over time. Looking at this from a more mathematical point of view, we consider a transmitted signal, U of t in complex baseband, S of t in passband. Under line of sight only, the received signal would look like this. So we have the transmitted signal, which is delayed by a certain time depending on the distance. If the receiver is moving, this distance would depend also on time. An amplitude, which depends on path loss and shadowing. Here the delay also appears in the carrier frequency, plus a Doppler shift. Okay, so the delay depends on distance, the path loss and shadowing are this amplitude, and then finally we have the Doppler. When we have many paths with many different angles, we will see the following. So now we have a superposition of different paths. Each path has its own delay, which can vary over time due to mobility. Each path has its own amplitude, which can vary over time. Here again we see the delay, and each path will have its own Doppler shift. Okay, this is because the different paths will have different angles theta. We can now pull out the carrier frequency here, and then we end up with this, where this is the equivalent complex baseband received signal. Okay, so again we have the different paths, the delay for each path, the amplitude, plus a phase rotation. And this phase rotation comprises the Doppler shift, but also the delay of the path multiplied by the carrier. So there are two different impairments here. In complex baseband, we can write the following expression, that the received signal in complex baseband is the transmitted signal convoluted with the channel. This channel itself has this expression. So there are n paths, each corresponding to a delta in the delay domain, with an amplitude and a rotation. If I substitute this c of tau and t in this expression, I will actually find what's highlighted in the green box. So the time varying channel is given by what is written here on the bottom, a superposition of deltas, each with a complex gain. In order to further study the channel, it's good to get a little bit more of an overview. In the middle here, we have the time-varying channel impulse response. And then we can, for instance, fix time and study only the delay. So we look at the channel at a certain time t and see what is the behavior with respect to tau. Then we know, for instance, already what is the notion of delay spread. Delay spread is the time between the first and the last path. Delay spread is something that you express in seconds. Well, typically you would express it in nanoseconds. The inverse of the delay spread is the coherence bandwidth. Okay, and this would be expressed in hertz or maybe megahertz or gigahertz. If we fix the delay and instead study the impact of time, then we have the notion of coherence time. So a given channel can remain more or less constant for a certain amount of time, and then it would vary. Okay, so the duration for the channel is more or less constant. It's called the coherence time, and this is expressed in seconds. The inverse of the coherence time is called the Doppler spread. This is how much the channel spreads in frequency. The coherence time has actually two different meanings, which I will talk about later. The channel is just physics. You have no choice of what the channel is when you operate in a certain environment. When you start communicating over that channel, then you have a choice, which is the bandwidth, b, or its reciprocal, the symbols, the duration. And then the channel will behave in different ways depending on our choice of b. So first of all, we look at a certain channel, Ct of tau given by physics, and we choose a certain bandwidth or its reciprocal, a certain symbol duration. Now we can ask ourselves two questions. Is the symbol duration much larger than the delay spread? If yes, then we have a narrowband channel. Okay, this is because when a very long pulse goes over a channel with a very short delay spread, it appears at the receiver as just a single pulse. It is as if there is no intersymbol interference. In the other case, so when the delay spread is larger than the symbol slot, then you will have intersymbol interference. Different symbols will interfere with each other. So if I send a single symbol, I will receive a blurred out version of this. And this is called wideband communication or frequency selective communication or dispersive communication. Okay. So the choice of t with respect to the delay spread determines whether the communication is narrowband or wideband. We can also look at t with respect to the coherence time. If t is very short with respect to the coherence time, This means that we can send many symbols within the coherence time. This means that this channel remains more or less constant for many symbol transmissions. We call this slow fading communication. So from the point of view of the communication, the channel remains constant for long times. In the other case, when the symbol duration is on the order of larger than the coherence time, we have something called fast fading communication, because potentially every few symbols the channel can change completely. So the choice of T or B, the bandwidth, will determine whether we have slow or fast fading and whether we have narrowband or wideband communication. And then any combination is possible. We could have narrowband communication with fast fading, wideband communication with fast fading, and so forth. In this lecture, we only talk about narrowband communication because it's the easiest one to study, but considering both slow and fast fading. To further understand the difference between wideband and narrowband communication, we look at the following extreme cases. First of all, a static wideband communication. This communication is wideband because when we look at this as a function of delay and time, for a given time the channel changes in the delay domain. So the communication here is wideband because there will be interference among different symbols. On the other hand, the communication is static because when we look at a certain delay, the channel does not change. So the communication is static, there's no change in the time domain, but it is wideband because there's variations in the delay domain. On the other hand, we could communicate in such a way that we have narrowband communication, so all the paths are arriving from the point of view of the receiver at the same time, but there are variations across the time domain. This is narrowband communication. In the next lecture, we will see the more general case where the channel can vary in delay and time. The difference between narrowband and wideband communication can also be seen in terms of what is called resolvable paths. We say that two paths are resolvable when their difference in terms of their time is much larger than 1 over the bandwidth. So in the figure here on the left side, all the paths here are resolvable from the environment. So the communication is such that the bandwidth is so large that each individual path is resolvable. So here, for instance, we see two paths that are arriving with only a few nanoseconds difference in delay. They are resolvable because my bandwidth is extremely large here, on the order of multiple gigahertz. If the bandwidth is very small, then the paths will appear as arriving at the same time approximately. So when I communicate with a small bandwidth over the same physical channel as on the left side, I would see something as shown here. So even though the channel has many paths, they all arrive at the receiver at the same time, because the resolution of the receiver is so bad, because its bandwidth is so low. The delay spread of the channel is a difference between the first arriving path and the last arriving path, roughly speaking. So in this case, the delay spread here is on the order of, let's say, 200 nanoseconds, same as it is here. The delay spread is the same. Whether or not we have intersymbol interference depends on whether the symbol slot is shorter or larger than the delay spread. In the figure on the right-hand side, the symbol slots are very long because the bandwidth is very short. This means that the second symbol will arrive here, so there's basically no intersymbol interference. On the left-hand side, with the bandwidth being very large, the first symbol may appear here, the second symbol may appear here, and there will be lots of intersymbol interference. So the delay spread causes intersymbol interference. It's important again to notice that the same physical channel was here used in both figures. The only thing that changes is how we use this channel. On the left side, we use a very large bandwidth. On the right side, we use a very small bandwidth. So from the point of view of the receiver, the channel looks very different. We now go into more details regarding the mathematical models of narrowband fading channels. So the first line shows what we know already from before. We have different paths arriving with different delays, with different amplitudes and different phases. In addition, we have the carrier and noise. In narrowband, the paths arrive approximately at the same time. because the receiver cannot resolve them. So all of these delays are the same. I can remove them like this. This means I can bring u of t out of the summation. Then I end up with the second line. The carrier, the transmitted signal, and then the sum over all of the paths. And for each path I have an amplitude and a phase. This whole thing is basically just a complex number which I call beta of t. So what I get in the end is just this thing. The transmitted signal multiplied by a time-varying complex number. Okay, so another way to visualize this is as follows. I have an input signal. I multiply with path loss, so that will reduce the power. Multiply with shadowing, which can reduce or increase the power. Multiply with fast fading and add noise. And then I get my output. If I were to visualize the received power as a function of distance, I would see something like this. So large variations as a function of distance, because the beta t varies very quickly when the receiver is moving. It varies very quickly because the phase phi n of t varies very quickly because it depends on the carrier. So I have these very large fluctuations in terms of power, even over very relatively small distances. Now what remains is to model beta of t. Once we understand beta of t, we are done. So we need to look into the statistics of beta of t. We can first make the following comment. The average power is determined by path loss and shadowing. Okay, so the average power level that we have here, for instance, 0 dB, is the value due to path loss and shadowing. Okay, so we know that the average power of beta is just whatever the path loss and shadowing gives us. Now we still need to go deeper in terms of the statistics. One thing is we need to look at the distribution. So what distribution does beta of t have? And at the autocorrelation, to what extent is beta of t correlated with beta of t a little bit later? One model for the channel statistics is Rayleigh fading. In Rayleigh fading, there is a transmitter somewhere far away, let's say here, sending a signal to the receiver, but without any strong line of sight path. Instead, the signal arrives via scatterers towards the receiver. There are n scatterers uniformly placed around the receiver. When the number of scatterers n grows unbounded, according to the central limit theorem, the channel will be a complex Gaussian, zero mean, and with a certain variance sigma squared for the real and imaginary part. This variance depends on the power due to path loss and shadowing. When the channel itself is complex Gaussian, the envelope has a so-called Rayleigh distribution. The Rayleigh probability density function is here shown on the left and the CDF shown on the right. The equations below describe mathematically what the density looks like. Just to know the terminology, under Rayleigh fading, the channel coefficients are complex Gaussian, the envelope is Rayleigh, and the power is exponential. So the Rayleigh just refers to the envelope. To generate Rayleigh fading, let's look at the following example. We first decide on a transmit power and system parameters. Then we generate path loss, given by the standard path loss equation. Then Pt times the path loss should be interpreted as the power due to path loss only, so averaged over the shadowing in the dB domain and over the fading in the linear domain. Then we generate a realization of the shadowing in the dB domain as a Gaussian random variable with a certain shadowing variance. So then the power Pt times Pl times the shadowing in the linear domain should be interpreted as the power averaged over the multipath fading. Finally, we generate the multipath fading power as an exponential random variable. Finally, the instantaneous power is equal to the receive, so the receive power is equal to the transmit powers times path loss times shadowing in the linear domain times the new exponential random variable. If we then want to generate the channel itself, instead of generating the power as an exponential random variable, we could also generate a complex channel gain as a complex Gaussian random variable with zero mean and this variance, given by the path loss and the shadowing in the linear domain. So some things to point out. First of all, the channel itself is zero mean. Okay, so all the power lies in the variance. The right-hand side is MATLAB code that you can copy and run, and it will generate the first 4 steps. The second model is a Rician distribution. We consider again a transmitter and a receiver surrounded by scatterers, but also now a line-of-sight path. For this channel, the envelope has a Rician distribution. This is because the channel itself has 2 components, a line-of-sight part and a non-line-of-sight part. The non-line-of-sight part is Rayleigh as before. So again, the envelope is Rayleigh, but the channel itself is complex Gaussian. The powers of these two are given by s squared and 2 sigma squared. S squared is the power of the line-of-sight part, 2 sigma squared is the total power of all the non-line-of-sight paths. The ratio between the two is called the Rician k factor. It is s squared divided by 2 sigma squared. When we fix the total power, so s squared plus 2 sigma squared, the k factor tells us to what extent is the channel a line-of-sight channel. When k tends to infinity, the channel is a pure line-of-sight channel, while when k is equal to 0, s squared is equal to 0, and the channel is purely Rayleigh fading. This figure shows Rician distributions, so this shows the envelope of the channel, for a total power equal to 5. We here see the density for k equal to 0, k equal to 3, and k equal to 10. When k is 0, the blue density shows the Rayleigh distribution. When k equals to 10, we see that the distribution becomes much more peaky around its mean value. This is because the channel behaves more and more like a line-of-sight channel. Note again that in going from k equal to 0 to k equal to 10, we are basically transferring power from the non-line-of-sight paths to the line-of-sight path. When k becomes larger and larger, the distribution becomes narrower and narrower around its mean value. The total power, so 2 sigma squared plus s squared, should be considered as the power due to path loss and shadowing combined. And again here, shadowing is a realization of the shadowing process. To generate Rician fading, we can proceed as follows. We fix the total power due to path loss and shadowing. Then we choose a certain k factor. Then we compute sigma squared and s squared as a function of the k factor and the total power. So we see that by changing k, we move power from either the non-line-of-sight part or the line-of-sight part. Then we generate the line-of-sight part of the channel, so taking the square root of sigma of s squared, adding a random phase, and we generate the non-line-of-sight part, so just as a Gaussian random variable with variance sigma squared. The total channel then is the line-of-sight plus the non-line-of-sight channel, and then we can also compute the power. This here shows a histogram of the power for various values of k. So we see that for k equal a very small value, the power has an exponential distribution. This is shown in blue. When k has a very large value, such as 500, the power is very concentrated around its mean value and tends to a delta direct distribution. So far, we have looked at the distribution of the channel, but not at the variation as a function of time. This is captured by the autocorrelation function. So when we look at the channel at the time t, and the channel a little bit later, what is the expectation of their product? We call this a of beta, t and t plus delta t. The figure here shows as a function of time 2 random processes with the same distribution. So they are both Gaussian with the same mean and the same variance, but as you can see, the red process is much more slowly varying than the blue process. So the red process has a very high correlation, the blue process has a very low correlation. High correlation is because when I know the process at a certain time, I can say a lot about the process a little bit later. While for the blue process, knowing the process at a certain time tells me basically nothing about the process a little bit later. We will always work with wide-stance stationary processes in which the autocorrelation function does not depend on the time instant t. In that case, the autocorrelation function depends only on delta t and is given again by the expectation of the product of the channel at a certain time and a little bit later. So the autocorrelation function depends only how much this little bit later is. Recall from the first lecture that we can take the Fourier transform of this and we obtain the power spectral density. So what do wide-stand stationary processes look like? On the left side here we see a process that is not wide-stand stationary. In order for a process to be wide-stand stationary, the first and second moment should be constant in time. The process on the left, we see that the mean is going down in time, so this guy is not wide-stand stationary. The second process, we have a mean that is constant in time, but the variance is changing in time. So again, this is not wide-stand stationary because as time goes on, the variance reduces. On the figure on the right, we show processes with a mean that is constant in time and also a variance constant in time. So this could qualify as a wide-stand stationary process. Here again, on the bottom on the left side, we show two processes in red and blue. The red process is very slowly varying, the blue is very fast varying. If you were to look at the autocorrelation function, it would look something like this. So as a function of the delay between two times, so again we look at the process at one time and a little bit later, as a function of this delay delta t, we can look at the autocorrelation function. For the red process, the autocorrelation function goes down very slowly. This means that at some delay delta t later, we have very high correlation. While for the blue process, autocorrelation function quickly drops to 0. So this means that for a small delta t later, we know nothing about the channel. We're now ready to use this concept of autocorrelation functions for our communication channel. So we again consider a standard Rayleigh channel. It then follows, after some math which we don't cover here in these slides, that the autocorrelation function is a Bessel function that depends on the Doppler shift and the lag. From this Bessel function you can compute the power spectral density and it looks as shown here. If you plot those two functions you get the two figures here in the middle. The power spectral density has a bathtub shape ranging from minus FD to plus FD. The autocorrelation function has an oscillating shape. Here the argument is FD times delta t, with the first zero crossing at approximately 0.4. This corresponds, when we substitute back all the variables, of a velocity times a delay difference of 0.4 lambda. Velocity times a delay is a length, so this means that when the user moves approximately half a wavelength, the channel becomes uncorrelated under the given assumptions. Both the autocorrelation function and the power spectral density can be used to simulate the time-varying nature of Rayleigh fading. The mobility causes a spectral broadening. We see that the spectrum is broadened because of the Doppler shifts. If there's line of sight only, it is really only a spectral shifting. A tone will move to a higher or lower frequency depending on the Doppler. The channel is approximately constant for delays much less than the first zero crossing. So for delays around here, the channel is approximately constant. This is related to something we call the coherence time. So the coherence time is used in different ways, and I just want to point this out. One way is to say the coherence time is the first zero crossing, the time to decorrelate. So when I wait this long, the channel has become uncorrelated. The coherence time is sometimes also used as 1/10 or a very small fraction of this time to decorrelate, and is then the time to stay coherent. So for a delay on the order of 0.04 divided by the Doppler shift is the time the channel stays approximately the same. And coherence time can be used for both of them, but they have different meaning. Some further comments. From this equation here, highlighted, we see that when the velocity grows, the coherence time will be reduced because the right-hand side has to remain constant. So faster mobility leads to less coherence time, leads to a quicker varying channel. Similarly, when the carrier frequency increases, that means the wavelength goes down, for a fixed velocity, the coherence time will reduce. So for a fixed velocity, the higher we go up in carrier, the shorter will be the coherence time. Another note regarding simulation. We can generate the Jakes model by taking independent Gaussian samples and filtering them with an appropriate filter to obtain the correct autocorrelation function and power spectral density. This can be done in the frequency domain by generating Gaussian random noise, taking the square root of this spectrum and multiplying and then going back to the time domain. Or we can take Gaussian noise in the time domain, compute the inverse Fourier transform of the square root of the power spectral density, and perform a convolution. In either case, we will get the correct statistics and we'll get the correct autocorrelation function. Finally, we introduce two concepts related to time-varying channels: the level crossing rate and the average fade duration. Z of t represents the envelope of the channel, which will fluctuate over time with a certain average value and certain statistics. Z is a threshold value. Basically, when we are below Z, we are in a bad condition. When we are above Z, we are in a good condition. The level crossing rate is the average number of times per second that the envelope goes underneath the threshold value. So it tells you how often the channel is bad. The average fade duration is the average time the channel remains bad, how long it is in outage, one can say. In many cases, these quantities are hard to compute, but for the Rayleigh fading case with Clarke spectrum and the given here average power, it is possible to quantify the level crossing rate and the average fade duration as a function of the threshold, the channel power, and the Doppler shift. Note that when the Doppler shift goes to 0, the level crossing rate is 0, you never cross, and the average fade duration is infinity. We are now ready to conclude this lecture. What we've seen so far is that we're able to distinguish between wideband and narrowband communication for a given physical channel. We were able to derive Doppler shift due to mobility, define resolvable paths, and express a general formula of time-varying frequency-selective channels. We then focused on the difference between Rayleigh and Rician fading and determined autocorrelation functions and power spectral density of wide-sense stationary fading processes.